In a previous video, we talked about developing our sampling plan and what it meant to have sampling error. We actually looked at this particular example here and the difference between a sample statistic, the average, and the population parameter. So let's actually revisit this particular example here related to the number of children. So suppose that a population consists of 6 families living in, let's say, Brentwood Circle, and you're studying the number of children in the 6 families. So the Clark family has 1 child, Walston has 2, Dodd has 3, Marshall 5, and so on. So when we look at first, how many different samples of 2 can be found? And this is where our combinations that we talked about in a previous video come back. So if we want to know from 6 families, how many different groups of 2 can be found, we're doing 6 choose 2. And we talked in our previous video about how to do that in Excel. And we also talked about how to do it by hand. So just to refresh your memory, here's how to do it by hand. If we are doing 6 choose 2, then that's going to be 6 factorial. So remember, factorial means 6 times 5 times 4 times 3 times 2 times 1. Just write this out here. 6 times 5 times 4 times 3 times 2 times 1. And then we have on the bottom of our formula, we have that we're picking samples of 2. So we have 2 factorial, which is 2 times 1. And then we have 6 minus 2 factorial, which is 4 times 3 times 2 times 1. So what we end up with is that these 2 cancel each other out because it's all multiplication. So it's all times each other, which means that we can remove the top and the bottom when they're the same. What we get is 30 divided by 2, which gives us 15 different combinations if we are going to have 6 families and take them in groups of 2. So let's suppose we take a sample of size 2. Well, that means there are 15 different possible samples we could take. Okay, so let's go through this. If there are 15 different possible samples we could take, then what are the number of children in the sample? Well, Clark and Walston, gotta go back and forth here. Clark and Walston, Clark had 1, Walston has 2, which means that for this particular sample, there are 3 children, and 3 divided by 2 is 1.5. So the sample statistic here is 1.5. If instead we took a sample that was Clark and Dodd, so Clark is 1, Dodd is 3, that's a total of 4, and the sample statistic here would be 2. So notice that whoever is in the sample is going to change that sample statistic. The sample statistic is a random variable. It changes. If there is Clark and Marshall, Clark is 1, Marshall is 5. That's a total of 6. 6 divided by 2 gives us an average of 3. And so we could keep going and populating this entire table, looking at the sample statistic for all 15 different possible samples that could be taken from this population. Okay. So compare this to the population parameter. The population parameter says, okay, if the entire population is these 6 families, and collectively we add it all up, they have 18 children, 18 divided by 6 families, we get a population parameter, mu, of 3. So if the population parameter, that true underlying average, is 3, and our sample statistic in that first sample is 1.5, there is sampling error here of 1.5. In our second sample, the average was 2. Our sample statistic is 2. The population parameter is 3. There's a sampling error here of 1. In the third sample, the sample statistic is 3. The population parameter is 3. We get a sampling error of 0. So we're recognizing that that sample statistic is changing. In this particular case, we can easily figure out what the underlying population parameter is. But what if it's not just 6 families in that underlying population, but what if it's all families? All families in the US or all families in Canada. What is the average number of children? Well, that's a lot bigger group. And we don't know that underlying parameter that we're trying to estimate. All we have is these different samples that we can take that give us different numbers. And so, as you can see here, here's the different sample statistics. All these different combinations give us different ones. So if we take all the different possible samples and we were to take these sample statistics, these X bar, we could create a sampling distribution. So just like we were taking values of X before and looking at the probability distribution, we can, in our frequency distribution with our histogram, we can do the same thing with our sample statistics. So suppose we have all possible samples, and here they're all possible samples of size 2 in our example, and that the mean of each sample is computed. That's what we have right here, the mean of each tube family sample. We could then find the distribution of all the means. So we could look at, here's how many had families of size 1.5, and here's how many had families of size 2, and we could start to get that distribution. Okay. And instead of being numbers here, they're the sample statistics. They're all averages that are making up this distribution. So we're getting a distribution of all the means. So sampling distribution of the sample means is a probability distribution, a PDF, just like we saw before, of a given sample size. So let's construct a sampling distribution. So we randomly draw all the possible samples of size n from a finite population. So here we had the 6 families. We drew all the different samples of size 2, and we found the statistics of interest for each sample. So we found X bar for all the families of size 2. Okay, so we're going to list that out. And that is what you see right here. Okay. The next thing we would do is we would say, okay, from this list here, how many 1.5s were there? How many 2s were there? How many 2.5s were there? How many 3.5s? And so on. So we're going to list in one column the different observed values of the statistic, and another column the corresponding frequency of occurrence. So creating a frequency distribution here. So for example, here are the different numbers, average number of children per household. And in terms of the 1.5, there was one sample that had an average of 1.5. There were 2 samples that had an average of 2, and 3 samples that had an average of 2.8. This was out of a sample size, this was out of 15 samples. So then if we take 1 divided by 15, we get the probability that the average is 1.5. And if we take 2 divided by 15, we get 0.133, the probability of having an average of 2. So we're doing just like we did before in our previous videos in terms of creating our probability distribution. So then we plot this probability distribution here, where here is the mean number of children, and here we have our frequency. And so we should know a couple things when it comes to sampling distributions and their characteristics. The mean of all sample means is the population mean. So when we take all of these X bars and we average them all up and find the average of the averages, then we get the population mean. So mu, our estimate for mu, is going to be the average of the averages. So if we take all of this list here, all of these averages, if we add all these together, divide by 15 to get the average of the averages, that's going to be our estimate for the population average. Okay. If the population from which the samples are drawn is normal, so we have a continuous random variable, then the distribution of the sample means will also be normally distributed. So we talked about in our previous videos in terms of x, our variable, if our variable, let's say age, is continuous, is normally distributed, remember, so we're talking about the fact that there is this centrality to it, the typical age there, and then we have a symmetrical here where we have kind of an equal number above that and below that. The average, the median, the mode are the same. If your underlying data, ages, has a normal distribution, then your distribution of the sample means your average ages is also going to be normally distributed. Okay. If the population from which the samples are drawn is not normally distributed, okay, then it is possible that the sampling distribution could be approximately normal as long as the samples are sufficiently large. So think about, for example, the coin toss that we talked about in a previous video, right? We tossed the coin. When we tossed the coin, it was heads or tails. So it wasn't a normal distribution because you only had two outcomes. It was discrete, and we had a binomial distribution, and we looked at that binomial distribution. So the population, the success, the number of heads in our coin tosses, that's not a normal distribution. It's a binomial distribution. However, our population parameter and our sample statistics, if we're looking at proportions, percentage of heads, if we have big enough sample sizes, then we can start to approximate a normal distribution, even though that underlying distribution for the original data is not normally distributed. So when we talk about sample size and how big should sample size be, we want our sample sizes to be big enough to be able to make that inferences. Let's go back. To make our inferences about the population, right? So we want to have enough entities within that sample to represent the variability in the population. And then when we start to then summarize the sample and we take into consideration that sampling distribution, then we can make that extrapolation. So the reason we spend so much time on like z-scores and normal distributions is because when we start to get into the sample statistics, then they can approximate the normal distribution for that. All right, so here we go. Here's our different household sizes. If we total up all of the different household sizes, so really what this all translates into is if I scroll up and you add this 1.5 plus 2 plus 3 plus 2 plus 2.5, add these all together, you get 45. 45 divided by 15, the average of the averages is 3. All of this that you see here is just doing the same thing, but it's doing it from the frequency distribution table, where it said there was one family at 1.5, so 1 times 1.5 is 1.5. There were 2 families with an average size of 2, so that's a total of 4. And so that's just putting it back to the list it was before and totaling it up to 45. 45 divided by 15, our approximation of the population parameter is that the typical household has 3 children. Remember, the average of the averages is your estimation for your population parameter. So mu here is estimated to be 3 based on finding the average of the averages. So what we're going to be doing is we're going to be looking at taking that sampling distribution and using our central limit theorem. Central limit theorem says if random samples are selected from a population with mean mu and a finite standard deviation, then as the sample size increases, the distribution of x bar approaches a normal distribution with mean mu and standard deviation. So we're getting ourselves to the point where we can start extrapolating to the greater population, and that is then identifying and measuring that sampling error and recognizing the importance of a sufficient sample size in order to make that extrapolation, which is why I bring you back to the videos we talked about before in terms of developing a sampling plan and the importance of determining sample size. So in those videos, we talked about when you have a survey, for example, how do you figure out how big your sample should be? We'll do some more discussion on sample size in our upcoming video.